There's a new state of stress. Again, that's the stress state at a point. This is all in megapascals. So we're going to do two things. One, we're going to draw the rotated stress state at max shear stress. And we're also going to do it at a 30-degree counterclockwise rotation. And we'll have some more reasons why we need to do this at a stated angle of rotation. So we'll begin to acquire the skills to do that. So we're going to focus on the Mohr circle approach, but we'll set up the equations. So we need a coordinate system to do this. So if we were to put this into the tensor on the x face, we would have positive 10. On the y face, normal, it would have negative 6. Shear stress would be positive 8, as I would be on the positive x face, and I'd have a shear stress going in the positive y direction. So we could do the transformation matrices. Right, we could get into the equations. Right, we'd be using sigma xx is equal to plus 10, sigma yy would be equal to minus 6, and sigma xy is equal to minus 6. So if we wanted to do that with the equations, begin. So if we wanted to use the equations and just sort of chug our way through, we would use those three values, and we'd be headed right here into calculating C, calculating R. Here we're interested in tau max. We would need theta S as well. So we'd be doing a little bit of equation substituting. And then after we had done that, we would be looking to do the known transformation. So then we'd be back up here, and we would be using an angle for our given theta. So if it was a 30-degree counterclockwise, it said, so we would have 30 degrees in the counterclockwise direction. This would be creating a positive slope. So for this, we would use theta equal to 30 degrees. So we'll just kind of go back up here for part 2. We would use theta equal to positive 30 degrees. Counterclockwise would be creating a positive slope there. So that kind of sets us up for the equations. We're going to do this focusing a little bit more on Mohr's circle. So we need our initial points here. So the Mohr circle canvas requires these 2 points kind of started off. And just remembering when I draw the axes in just a minute, tau is clockwise positive. So on the x face, we've got 10 in tension. On the y face, 6 in compression. We have a shear stress on the positive x face that would be causing the element to rotate counterclockwise. So we'd end up with a negative 8 and here with 8. So we're going to remember these. Actually, what we're just going to do is bring it with us down here. So we'll create a canvas down here. And so we'll put on the vertical axis is the shear stress, where clockwise is positive. We've already actually applied that. Already prepared a Mohr circle canvas for us. All we need to do is plot our 2 initial stress points. So the x was at 10 minus 8. The y point was at minus 6 and 8. So right about there would be y at minus 6, comma 8. So we're just going to connect those 2 points right about there. And from that, we've now defined the center and the radius. We've just got to do some very simple calculations. So the center is at minus 6 plus 10 divided by 2. That gives us 2. So I'm just going to label it right there at the center. Got a chance now to do the radius of that circle. So I've got now a side of 8, an R, and this goes from 2 to 10. It's off just a little bit, giving me a length of 8. So that would mean that R squared is equal to 8 squared plus 8 squared, giving us r equals 11.31. So we're going to draw the entire Mohr circle here, see if we can do it nicely. And so we get a picture, something that kind of looks like that. And in this problem, what we're interested in is tau max. So by picture, we've seen those are the principles, right? Sigma 1 and sigma 2. And that up there would be the position of tau max. So we're going to end up tau max is equal to r, which equals 11.31. So at that point, right, as our stress state is sitting at maximum shear stress, right, we would have a shear stress of 11.31. Right? All the stresses, all the normal stresses are going to be equal to 2. And so let's just go through and see how we find that angle. So I'm going to take that x point, and I'm going to strike it all the way up there, and that would be 2 theta s. So we get a nice easy calculation for the pink theta right there. It's on an 8, 8 triangle. So if we look at our equation that we're just about to have here, it's going to be that 90 degrees plus the pink theta would equal 2 theta s. Right? So if you were asked for it, you could go ahead and solve 90 degrees plus 45 degrees equals 2 theta s. So theta s equals 67.5 degrees counterclockwise. So let's just go ahead and draw the stress state that results. So I'm going to draw this cube, and it's going to be at a really steep angle right here. And so I've just taken that thing to 67.5 degrees. So this now is where the x prime face sits. So the answer on all the faces for the normal stress is going to be 2. So I'll label those 2. Right, the answer for the shear stress, right, on the x prime face is going to be positive, which is clockwise on Mohr circle. So on the x prime face, I'm going to draw a shear stress that would cause the element to rotate clockwise. And if I can do it on one face, I can do it on all the faces. So we'd end up with a 11.31, and this would all be in megapascals. So the second part of the problem asked us to rotate this 30 degrees counterclockwise. So on Mohr's circle, that rotation would take us 60 degrees. Right? Angles on Mohr's circle are twice what they are in real life. So what we want to do is take that x point and strike it through 60 degrees, putting it approximately right there. Right on the other face, our point is sitting right there. So what we want is the coordinates of these points. The coordinates of those points are going to be the stresses on our face. So we're going to attack a triangle here. We know that the pink theta, right, came from a 45 degree triangle. So what's left is going to be 15 degrees sitting right in there. So I've got a good triangle for us to analyze. So the location, right, the location of that top point is going to be the stresses on the x prime face. So I'm going to redraw this triangle below. So I've got a big triangle. I'm going to draw it extra big. It has a 15-degree angle. All right, again, this is on a horizontal axis. So that's sitting at sigma is equal to 2. I know that r remains. R is still 11.31. And what we want is the location of that point right there. So we've got a need for perhaps an L1 and an L2. So how would we deal with solving for those? We're just going to use simple trig. So the sine of 15 degrees is equal to L2 over R. So that just tells me that L2 is R times sine 15 degrees. So that's going to be 2.93. Let's go ahead and write it right there. All right, similarly, you can use a cosine. And if you use that the cosine of 15 degrees was L1 over R, that would give us L1 is equal to 10.92. So I know the coordinates of this point now. In the x direction, it's going to be 2 plus 10.92, 12.92. And in the shear stress direction, it's going to be 2.93. So I'm going to draw my rotated stress state. And that is going to be the state of stress on the x face. So let's go ahead and draw this thing, this rotated stress block. "30 degrees is what it's been rotated in real life. So on the x prime face, I've got 12.92 normal, right, 12.92 on the other side. I have a positive shear stress, and Moore's circle sign convention says that clockwise would be positive. So I can draw all 4 shear stresses, and I know their value, so I'm going to call them 2.93. And I've got one more thing, a normal stress on the y face. So this thing also ends up down here. The coordinates of that point down here would be 2 minus 10.92. So it's going to be minus 8.92, comma, minus 2.93. So it tells me that I'm going to have compression on the y prime face. So I would have a stress in called 8.92. So that is the rotated stress state at 30 degrees counterclockwise.